as I said, the whole point of connecting half cells together is so that we can work out the potential difference that could be generated from a certain battery, perhaps. So let's take a look at what's happening. First thing is there's an equation on your information sheet that goes E cell is equal to E cathode minus E anode. In order to use this, you first have to identify the anode and the cathode, which normally means you first have to identify oxidation and reduction. And these are it can easily be muddled, and the statistical chance of stuffing it up is quite good. So I choose never to use that particular reaction at all because it just confuses the world. So it is on the information sheet. You're welcome to use it, but I'm not going to teach you using it. So ignore it from here onwards in my teaching. I'm going to tell you what I'm going to do. So the first thing is calculate the cell potential of the electrochemical cells containing iron and copper half cells, and it's the iron to 2 plus and the copper to 2 plus because there are some other coppers and irons on here. So let's first identify what we've got. I'm going to make this a little bit bigger in the middle, about there, and then let's look what we've got. We've got the copper half cell over there, and we've got the iron 2 plus half cell. I think I might have just stuffed this up. There it is, okay, over there. So those are going to be the two half cells that we are interested in. As I've said to you before, the top one is going to be your anode, the lower one is going to be your cathode. The top one is where oxidation takes place, the lower one is where reduction takes place. The top one we write backwards, the lower one we write forwards. So this is how we're going to work out half cells. And if I'm going to calculate the cell potential, the way I like to do it is as follows. So I write iron becomes iron 2 plus 2 electrons. I just wrote that backwards. If I write something backwards, obviously something like the potential difference it would generate would change its sign. So because I've just written it backwards, instead of writing negative 0,4, I'm going to write positive 0,44. The copper, on the other hand, Cu2 plus 2 electrons, gives me copper metal. I've just written forwards, so I keep the sign exactly the same, plus 0,34. And then I simply go 4 plus 4 is 8, 7, 4 plus 3 is 7, and my cell potential for that cell is 0,78 volts. And I find that much easier than trying to work out whether I've got an anode and a cathode and putting them in and then getting the minus sign confused and all sorts of things. All right, so that will be the method that I will use. If we take a look at the next one, an electrochemical cell consists of aluminium and silver half cells. So let's identify those guys quickly over here. Aluminium's quite near the top, there it is, and silver's quite near the bottom, there it is. Okay, so I'm going to write the aluminium backwards, so it's going to go Al goes to Al3 plus 3 electrons. And I've written it backwards, so I better change the sign. It becomes plus 1,66. My silver I'm going to write forwards. Remember, backwards, backwards and then forwards. So my silver I write forwards, Ag plus a single electron gives me Ag. The value there is plus 0,80. Now, in the last example, I had exactly the same number of electrons. I had 2 electrons in the one and 2 electrons in the other. This time I've got 3 in 1. If I want to get a balanced equation, I better balance out those electrons, which means I need to put a 3 here, a 3 here, and a 3 here. When you do that balancing, you do not multiply this by 3. You keep it untouched. And now we go 6, 8 plus 6 is 4, 2,46 volts for that particular electrochemical cell. If the E cell is positive, it means the reaction is positive, at least is spontaneous. And if you get a negative value for the E cell, the reaction is not spontaneous. So now we have to predict whether the following redox reaction is spontaneous or not spontaneous. So in this case, what they've done is they've actually given us an order of events. I have to go Fe2 plus to Fe, Fe2 plus plus 2 electrons becomes Fe. And that is going to be written forward, so it's negative 0,44. Because I had to go from 2 plus to no charge. Then I'm going to look at the copper, and the copper is going to go from copper metal to copper 2 plus, which means I have to do this one backwards. So it's Cu becomes 2 electrons plus Cu2 plus. And because I just wrote that backwards, I better change its sign, negative 0,34. Which means that I have now got a negative cell potential, and therefore that is a non-spontaneous reaction. And finally, this slide is a slide that has no place in the curriculum, but I'm going to show it to you anyway. It's called the Solubility Rules, and somewhere along the line they kind of expect you to know what the solubility rules are. The reason I'm bringing it in now is because we now need to think about various solutions. We've got copper solutions, and how would copper deal with being in a sulfate versus being in a carbonate versus being in a nitrate. And obviously, if we want these things to conduct electricity, they need to be soluble. In other words, they need to dissolve in water. So we have to consider the fact that all nitrates and acetates are soluble. This is true. All alkali metal salts and ammonium salts are soluble. That's very handy to know. Okay, I'll tell you why in a second. Then, it goes into a whole lot of details. All the chlorides and bromides and iodides are soluble except for blah, 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 blah. All the sulfates are soluble except for blah, 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 blah. All the carbonates, phosphates, and sulfates are slightly soluble except for those with the blah, blah, blah. All hydroxides, and if you think about it, alkali metals and ammonium metals were already all solid, so at least soluble. All hydroxides are very slightly soluble except for those of the, and we just knew that alkali metals and ammonium salts are very soluble. All sulfides, except for those of the alkali metals and alkali earth metals and ammonium, are extremely low and sorry. So it's a lot of blah blah. I would never bother learning it. I have never bothered to learn it. But what it does say is that there are some rules for how things dissolve. And so when we are working out what solutions to use for conductivity, we need to get soluble solutions. And this is your key. If you're trying to find a potassium, at least if you're trying to find any solution, I would always. So what solution is good with copper? Copper nitrate. What solution is good with iron? Iron nitrate. What solution is good with silver? Silver nitrate. So always choose a nitrate because it will always be soluble. If you are looking for a metal that's always soluble, I like any of the alkali metals. Which one's the easiest? It's potassium. And for this reason, when you are asked what is the best solution to put into a salt bridge, potassium nitrate. Why? Because it's going to be soluble in every solution and it's going to conduct ions across that salt bridge. So just always keep in mind that potassium nitrate is the best stuff. You can use other stuff, depends on the exact cell, but potassium nitrate always works. Why? Because all potassium salts are soluble and all nitrate salts are soluble. So you're not going to stuff up your cell by making a whole lot of solids that precipitate out of solution and stuff like that.